Yeah, what I would like to talk about today, thanks for having me. I'm from LAION, and we work on various kind of open foundation models, open in the sense that we usually have the whole pipeline in open form, so the data set, composition, training source code, the model open weights, and also importantly, forgotten often evaluation that is reproducible. And now we are having thoughts how to actually progress on this front in terms of actually making stronger, scalable foundation models that are doing better in terms of, say, generalization if you invest in pre-training or post-training compute. So for this, we try to go the scaling law derivation direction. I will have some hints, hopefully, in the talk on that. So I think the sad situation still is that despite we had a lot of breakthroughs in the transferable learning, arguably before in zeros and 90s, the old machine learning was always, okay, you pre-train a narrow model, you can only perform on a narrow task. If you try to go a bit on the outside, immediately everything collapses. You have to redo everything again from scratch. We don't have the situation now, and these are the so-called foundation models as artifacts of this breakthrough. However, so most of them are trained in the industry labs behind the closed lab. So the strongest models of this kind are not really available for research to study this strong function that they show, especially the transfer. Yeah, Europe is one thing. So we haven't delivered as a continent a strong model of this kind yet. But also in US, if you take a look on academia, there is a big gap between the open source and closed lab still. DeepSeek moment was there, yes, but yeah, and especially in multimodal direction, there is still a lot to do. So these foundation models exhibit scaling laws. We heard about them today, which means that you have a very clear regularity by investing in the compute that is in a data set scale, in model parameters during the pre-training, and the important core capabilities of the model. So the more compute you invest during pre-training, the better generalization. So the claim, the better the transfer. Here, the old paper that was measuring this only on test loss. Nowadays, you measure it rather on downstream tasks, to be sure. And the scaling laws are not only giving you the idea that your learning procedure, or the subject of your study, behaves this way, but also give predictability about various important model functions. So you can predict for each compute scale, for instance, how many data samples and how large the model scale should be to be in a compute optimal regime, so that the compute you invest leads to the best possible performance achievable with those parameters, and those are predictable. So the problem is that even the scaling law studies that are executed on smaller scale regime to first derive this predictable model are so intensive that usually still we don't do it often in academia. So, and to do it also in academia, you need this fully open pipeline. So you need reference scaling laws that were executed on the open data, because if you measure scaling law on a data set that is closed, nobody else actually can reproduce it, so it loses their reference character. So there were a couple of organizations that out of despair, more like grassroots character, came early enough, 2020, 2021, across the world. So LLM in US that invested a lot in making the language pipeline open, and then LLM caught up and did even more work into this direction. So like LLM harness is a industry standard for language model evaluation, thanks to LLM. On European ground, there was a Sparkle, big science, driven mainly by Hugging Face people, with an attempt to replicate GPT-3 level back then by Bloom, which was a good thing for you to happen, but kind of faded out. And unfortunately, on the dataset side, there was not really something released that was reusable afterwards. Apart from the fact that the model that was undertrained was not actually then useful for the community further on. So LAION came around the same time from the multimodal direction right from the start. So we did a lot with language vision, mostly contrastive pre-training, so clip, also clap for audio, and from the start we were then attempting to put also the data sets entirely open so that people actually can reproduce and build on the top of the results obtained with the study. So in certain sense we have now, oh yeah, now the picture is correct. It was not correct before, so it seems to be repaired. So in certain sense now we have actually some fully reproducible pipelines for important model types in the foundational class. For instance, for CLIP, you have Reliant 5B or Datacomp 1B or DFN that are fully open data sets. You need to still obtain them on your own, but the whole procedure is fully open, so you can do it as a research lab. You have OpenClip as a source code for training. You have also pre-trained open weights models that you can immediately touch and study if you do not want to play with pre-training. And you have also OpenClip benchmarks that are open and fully reproducible. So this kind of studies require those supercomputers. So that's why we were early on sitting on machines like Jules Booster at ULI Supercomputing Center, and also went to US via Insight program to an old machine summit, but that also helped. So we are trying also to get this a routine exercise to acquire resources on large machines and use them for the open source community to get this important pipelines done and open. So, and what is it good for? So again, coming back to the, so actually it's a story about learning procedure comparison, model comparison. So in the heart of machine learning, using scaling laws. So one of the earlier works we had was about looking actually at dataset comparison quite clearly by using the very same learning procedure as OpenAI did to train a clip, copying it as much as possible algorithmically, and then using a dataset, open one, called LAION 400M or LAION 5B, two different versions, to see actually how this compares if you attempt to derive somewhat like a, not full version, but somewhat existing version of a scaling law for the two data sets. Well, the closed one, you could take only the points that OpenAI gave you, 3 points. Fitting a line with 3 points is a bad exercise for every physicist person, but yeah, you don't have a choice. But we could measure at least for LAION as much as we could back then. And then you see trends like this, now backed up, but by the scale span across order of magnitudes here, 3 and compute, showing that, for instance, for an important downstream task, a zero-shot ImageNet classification, you have at smaller scales somewhat an advantage of the LAION data set, but then it is line crossing, and you see that the larger scales, then the width, the closed one, takes over. So you can be sure, if you measured it accurately enough, that in terms of scalability, this width data set of nature is unknown, offers better scalability, and you can try to tilt the line of the data set that you use then in a controlled manner. So on a different downstream task here, retrieval, it might look entirely different. So it is also then a story that if you do data set comparison, it has also downstream task dependency, which then now poses all kind of interesting questions. How do you combine a canonical data set that would be good across all downstream tasks? But you see that the scaling tendency is the same. It always improves on downstream tasks in terms of the performance, although the scaling coefficient is different task-wise. So here you would prefer the LAION data set to train on, because both the offset and also the slope shows you that it's a better choice in terms of scalability on the downstream if you invest more compute. This is also the story about being a frontier lab. So we have to catch up in academia with this trend to get actually the models not only trained in the open manner, but also trained up to the somewhat reasonable level of performance that can be considered state of the art. Because only then can you actually study the strong function on the level interesting actually for the research and the industry community, okay? But in academia, you have to reach up somewhat. There can be a small gap, but at least matching the level of this generalization and transferability that the closed lab models are showing. This is what we were able to do with open clip reproduction. If you look at the numbers, and importantly, this is now aligned on compute. So it's not now saying, okay, we reached X% on a downstream task, but it's X% given a controlled budget. So we can be sure that our procedure is equivalent to the procedure used behind the closed doors, because we know that the same amount of compute spent on it leads to the same results. And this is very important. This is why scaling laws are so important. There you can make sure that you don't compare anymore in isolated reference points on some arbitrary scales, but you control under also controlled conditions. So you compare under controlled conditions, and you can be sure that your method is now spending the same amount of compute leads to the same result. The same with the data sets. So there you have to be able to catch up with same scales that are used for these experiments that we were able to do with LAION 5B back then, already 3 years ago. Another hint that this kind of works can be successful is that you can track your usability, for example, via Hugging Face downloads. And this is what we should strive also as academia, that is not only research artifacts, but also picked up by people with a side effect that you can track whether your benchmark performance actually corresponds to the model quality. So if your models can track up millions of downloads even each month, then you know that indeed they have something that is of interest for people, and then that means that they have a level of performance that is decent. So the same we were doing with our collaborators from Washington University and LNAI back then, now Stanford, Ludwig Schmidt. This is the well-known work, I think, meanwhile, on DataComp-LM, DCLM, that led to an open data set, DCLM baseline, that many people are using. LNAI used it also in OLMO 2 as one of the biggest parts of the mixture. So, and also here, this is not a full scaling law. These are scaling trends. So you measure on some reference points and scales, but what it gives you is an idea, how do you compare with other efforts that also have invested in a known amount of compute on certain reference scales. And if you see that the slope defined by those points is somewhat decent compared to the others, then you know that you don't do so much wrong. So then you can continue going to the larger scale. So this is an important sanity check, although it's not a full scaling law. What we do now in a frame of Open EuroLM together with OpenSci Collective, that is a branch of LAION, we try to establish such set of reference baseline models to provide sanity check grounds and allow this fair comparison on a light compute data. So we take different impacting reference data sets. So here they are listed, 7 of them: DCLM, Nemotron, FineWeb, EduPile, Slimper, all the ones, C4, I mean, old but gold in the sense because they can still serve as a reference for comparison. So, and you do then measurements across different model scales with token budgets. Here only 300 billion shown, but we did it also for smaller ones, 50 billion, and for higher ones, for the top performing data, for 1 trillion. And then you can have this data set ranking that is also spread across different scales so that you're sure that what you see is consistent. So it could be that on one particular scale, the ranking looks this way, on another way. So what does it tell you in the end? Here you have a glimpse on consistency, which is again not a full scaling law, so it's a way towards this. And this consistency helps you also to actually do, again, sanity check comparison. For instance, here you see that some attempts like training 1.7 billion euro LLM model, that is a multilingual attempt. If you compare it to the English dominant references, for example, trained on FineWeb, which is the red marked line there, you see that way less compute for FineWeb Edu. So these are like 300 billion tokens with the same model scale, 1.7B, lands up on the same level of performance. Although the English related compute, so EuroLLM used around 2 trillion tokens, this used only 300 billion English tokens. So actually, also vastly different, vastly larger compute for the English. So this reference comparison gives you a note, okay, you have to fix something about this particular training. So there the compute is burned, the English performance for some reason is not on the expected level. So that's why I'm arguing for the establishing references like this, that you know where you stand and you know what to improve. We also look into the direction of the scaling laws for reasoning models. Very first steps, gathering data. Again, our co-work, again, with a huge amount of collaborators. This is, again, work mainly driven by Ludwig Schmidt's labs and friends. And there you begin to also estimate scaling trends depending on the data size used for the post-training on the reasoning traces. And again, you can compare yourself with other efforts that were investing similar amounts of compute, similar amounts of data, and trying to derive from these the ablations necessary to improve on the current state of the art. So following these recipes, we were then also able to train this model we call actually OpenThinker 3, which OpenThoughts is the dataset, OpenThinker is the model, that using SFT only, no RL, is able to outperform or match most of the reasoning distilled models from the big DeepSeek R1 brother. Back to the full scaling laws. So why should we care about deriving them, and what can it in what form can it help us actually to do progress in open foundation model quality? So if you look, so this is a toy picture. Two hypothetical procedures: in orange, learning procedure 1, in blue, learning procedure 2. And if you would measure this story on some isolated reference scales on the upper range, on the smaller compute scales, you would prefer orange. You would say, you would prefer blue. You would say, okay, the gap is so vast. And then if you look at the zoom out of this, these lines would almost look parallel, and you would see no tendency for the crossing. So this is what most people usually do, because this is also cheaper. But what you rather have to do is not necessarily going to the largest scale possible, but at least doing dense measurements in this smaller scale span, so that you can estimate the crossing point and can tell that the orange is actually a better scalable method, that on the absolute higher performing range, which actually matters for you, if you are not interested in this upper scale where there the absolute error is high, you're interested what happened downwards. So when you are actually interested in estimating these crossing points, this can be done only if you do dense measurement to derive the full scaling law in this form. And this is what we did now in our current work that we put on arXiv very recently, comparing as an example two different language vision foundation models, CLIP and Mammoth, with the only difference that CLIP is contrastive only and Mammoth is contrastive plus autoregressive text, so captioner loss. So, and we did these dense measurements across various combinations of model and sample scene scales, especially on the smaller scale region, which is cheap. And from that, we can show that we can estimate this crossing point and decide that actually the blue, so which is namely corresponding to Mammoth, is a better scalable method on an important reference data set, datacomp 1.5b, 4b. The same we can do on other open data sets, on LAION, on DFN, right? So, and we can also make sure that these predictions are valid by testing the accuracy of the predictions on the held out points. So it's not now any more arbitrary scaling trend, which you might trust and might not, but you actually test it on the measurement that you did and make sure that the trends that you see are actually backed up by the accuracy. So following this, what we saw from the scaling law derivation-based comparisons, we then took this advice that Mammoth is actually better scalable and trained a model on the predicted larger scale with performance that was then projected to be matching or even stronger than closed models that use the same compute and a similar architecture in the language vision domain. And we indeed saw that we can reach up almost to the level of the closed SIGLIP2, which also again validates this method of comparison via scaling law derivation. How much time do I have? Okay. No. So the scaling law derivation, of course, can give you only as much as the score on the downstream tasks expresses about model quality. If the benchmarks evaluations are broken, then you go into direction of a supposedly better model quality, but probably it is also off. So we have also some work done in the direction of improving the evals. Here, as a warning, what we see also for the current reasoning models is that you confront them to the variations of very simple tasks. On the top, you see the rough form of the task as a template, and then all variations are just changing the natural numbers in the question. There is nothing else. So there is no adversarial trick here, nothing. It's a perfect natural language math related task. And what we see, to our surprise also, is that with this really background elementary arithmetic like task, you can induce very strong performance fluctuation in correct response rates, even for the strongest models. So if you look at the DeepSeek R1 performance, this one that reaches almost correct response rates of 100%, the red one is corresponding to variation 4. And then you have something that drops almost down to 0.2, that is bluish one, variation 5. And the only difference are just the two natural numbers. So this hints, of course, that, and then if you look at the DeepSeek R1 performance on the graduate level, Olympiad level math tasks, you see there are quite high scores that kind of convey the impression that this model is very powerful in generalizing to that level already, which is obviously not true if you look at the effect of the variations in the simple task here. So we need to improve also the evaluation routines that we detect such weaknesses. And yes, a question. The contamination for we could only do it for the cases where there was open data. So we could see, for example, for S11 or for Limo, which uses very small amount of data to train, and that were starting from Quen 2.5. For Quen 2.5, if you test on this task, is almost, I don't show the Bayes instruct model, but it's almost zero. So there's not, it does, for some reason, it doesn't solve it. If you introduce this 1,000 examples that have nothing to do with this task, you see that the rates are elevating, but you still see the fluctuations for some reason. So you kind of can be sure that there is not a consequence of contamination, but you also see that despite the improvement, the actual problem with zero-shot generalization is persisting. So you should be able to address this task to some extent in a uniform manner, right? Either you are bad in uniform or you're good in uniform, but you shouldn't fluctuate wildly only because you change two natural numbers. You're keeping the whole template absolutely fixed. Yeah. So, so what we would like to do also in frame of upcoming EU projects like Open Euro LLM on Elliot, together with, for instance, people from Tübingen, Alice Institute there, Tübingen AI Center, but also other European partners, is to gravitate towards this multimodal foundation model that is also able to produce actions at outcomes, so an agentic appeal of it, that would be stuck of such components with validated scaling laws. So we cannot afford to train it from scratch, even if we get all the compute in the world right now, but having validated pre-trained components will help us to hopefully dedicate somewhat less compute in the post-training of such a model in lava-like manner, for instance. However, still, if you we need open Bayes models for this, and if you would like to replicate something like DeepSeek V3 and DeepSeek R1 together, you would need, for instance, about 1-2 weeks on the whole Jupyter just for single training run. So we need here to talk to both EuroHPC and maybe to friends from Swiss AI to bind the resources on such effort at some point to allow for the moonshot, because each of the single machines cannot actually offer compute enough to conduct this kind of training without waiting months for the outcome to be there. So we would like also to argue for this open source foundation model and dataset alliance that would bound then the people who actually built such artifacts, both datasets and models already, that have a track of experience on that, but actually just need a better strategy to align what is now the most important priority to go for as a model type, and how to apply together for the compute necessary for that. So this would probably generate a better push also for acquiring computer resources if we would do it just all alone, and also then repeating. So there is a lot of repetitions in all of these efforts we see, right? So maybe it is better to talk together scientifically, technologically, and get things done without also double work and avoiding mistakes altogether. So hope the scaling law for comparison story was a bit illuminating, and I would like to thank the people involved in LAION network, especially the core researchers. Mariana is sitting there. Ludwig is too far, couldn't come, but talk to us, come to LAION Discord server to exchange, and hopefully you can build this open, robust foundation models internationally and common effort. Thanks. Yeah. Yeah, very flexible. So actually, Mariana can tell you a lot. She's first author on this paper. And there we actually abandoned the very simple form of the scaling law that gives you just a straight line on log by introducing saturation terms, which was already done in the community. But obviously, this is, this is a functional form. So the way how you test it should be this way. So you should actually think about various functional forms that could be good or bad for fitting the measurements that you take, and then also think how to take these measurements actually. So it's actually a physics problem, I guess. And then you should evaluate each of these functional forms in terms of the error on the held out errors. And then you should decide which functional form describes better what you see. So, I mean, I wouldn't even say that power law is like the one holy grail to go for. There could be better ways to describe the phenomenon. As long as it's better predictable, then this is the way to take. This is the form to take. Yes, yeah, like in standard machine learning, yeah, you have to have basic. So the trouble with scaling law derivation, usually it's very new, very fresh, yeah, but still, a lot of us are just fitting through the measurements and reporting the error on the fit for the fit. So this is you don't know how bad you are for the points that you haven't seen. So, and this has to be improved. I mean, you're reviewing NeurIPS right now. I saw a lot of papers that exactly try to repair this. So it seems that this is a message that was received. Yeah. 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 So actually, part of OpenR1 are open source data. So we kind of didn't really manage to cooperate on this. I also wonder why it's also a bit, but at least we were pinging each other. So the OpenR1 to parts of that, then they actually helped to clean open thoughts a bit. And open thoughts took some hints from OpenR1. So there was some exchange, and actually, yeah, it was going in the common effort direction. So hopefully a bit more. Yeah. Yeah, the way forward is this. So for deciding how to improve on the car, so first of all, you have to have a reference for what you claim to be a strong open foundation model in form of such a scaling law. So if you say, let's call it now a CLIP instantiation currently existing, if you say that CLIP for you is a strong foundation model, then you should derive a full dense scaling law for this to have it as a reference. And then if you say, okay, I would like now to improve on the top of the clip, you do ablations using scaling law derivations. So you say, okay, I think the clip can be improved by captioner loss. Then you add up a captioner loss, which is Mammoth, and you derive a scaling law with as few measurements as possible, hopefully. And then you have a look how it actually compares to the green line, which was the reference. And if you see a trend for better scalability, then you're actually sure that it's worth going with to larger scales with it. But you have to have a reference, because if you would not have a green line, you have just the blue line. Okay, it predicts you what happens on the larger scale, but how do you know what have you improved or whatever? I mean, you don't know anything. So there should be a set of reference scaling laws like this for each important foundation model class. And then based on this, people should do in common action interventions. And these references are open. This is important. It's not like you measured it and you say, but sorry, I cannot give you the details on this. So if you begin to work on your own, you have the scaling law formed of somebody, but you actually do not know what they did to arrive there. You don't know the data, or maybe some algorithmic interventions are not known. So you actually cannot really compare. So the way forward is to open the pipeline to derive scaling laws on the important model classes using the open pipeline. And then every improvement is you derive yet another scaling law and then check whether you are better or not than the reference. If you are better, you report it to the community that they can check it also.
Really making me feel FOMO. But how's the FOMO alliance actually going to work exactly? Could you just tell me a little bit more about that?
The FOMO what? The alliance. Yeah, don't worry, you're not FOMO on FOMO. So I mean, this is like just the initial thoughts. So we talked to various people who are actually building this kind of models or creating the data sets. And everybody was saying that, yeah, compute is always a bottleneck, and then how to apply for that and whatsoever. And we realized that very practical thing here is to make this a bit more routinous and equipped with more people sitting behind it, so that there is no each time a big turmoil. Okay, who is applying for what? Who is the PI on which? How do we manage that? So it should be like a very boring and steady procedure where you equip this community with large amounts of compute. The only non-clear thing is that how people will arrive to a consensus what to train, right? So there we still in the beginnings of trying to understand how to arrive to this alliance. It is different to the other AI alliance that is more from the industry side, where I think for them it would be hard to talk about open data, for instance. And academia we can. And also this is more focused again on resource acquisition. So let's try to coordinate that it doesn't take a year again to bring the right people together for writing grants. Yeah.
I was wondering if you could comment about the drastic approach versus the genetic approach for.
Yeah. So you mean why it happens this way? Yeah.
Why the drastic approach? Why not generative?
Oh yeah, you could. I mean, so this is the fun thing. So if you think generative is better, just derive scaling law for it, show that it crosses both lines, and say, yeah, why would you care for contrastive plus captioner? So autoregressive poor is the way to go. But I mean, there is now a way to prove it. Before you can just say, okay, I would like to train autoregressive. I train it and I show on 1 or 2 points some numbers from benchmarks, but what does it tell you then? So if you cannot estimate accurately the trend, you actually cannot compare the models. This is our claim here. So this is a work about model comparison. It's not like a work about, so Mammoth is now the best thing to go for. It's a work that shows that if you're curious what is actually better than any other reference, how to actually figure it out. So the way to figure it out is to derive scaling laws this way. Also with offering this validation check. So I don't show everything, unfortunately. So we checked it on many reference data sets. You see, so you repeat the same scaling law derivation and you see the same consistent trends everywhere. Then you are sure that your method now is indeed better. And because you did ablations in such a controlled way, you know that the only thing that you did is just plugging in this captioner loss. So this is probably the reason why you see the increase in scalability. So it's a bit tedious, of course, because you cannot do one ablation at a time. So we need to improve, of course, on that, especially on the efficiency of scaling law derivation. You cannot like afford to put 1 million GPU hours, which we did each time to derive a scaling law. So, but it is possible to do it better. So you don't need to make very dense measurements like we did.